we can reproduce this solar abundance pattern. And this is summary, but the summary is not so interesting. I'll show you animation. I'll show you two animations. One is the result for the SFHO, and another one is the result for this DD2, green one. First, I'll show you how the electron fraction evolves in this FHO case. This is for the orbital plane, and this is for the meridional plane. As you can, sorry? Electron fraction. As you can see, as the shock goes away, the low electron fraction region is destroyed due to the weak interaction. But on the other hand, if you see in the meridian plane, because the ejector expanding in this direction is due to the shock heating, this electron fraction in this region is at first neutron poor. This is for entropy per baryon, not temperature. This is for entropy per baryon. As you can see, in the case of the SFHO, mass ejection is mainly driven by shock. And as neutrons oscillate, we have several shock waves like this. On the other hand, for the less compact case, in this case, the tidal effect plays a role, and the shock heating is not so strong. We have tidal tails and the tidal component. On the other hand, we have in the meridional direction, we have higher electron fraction. And in this case, there are two components, tidal one and shocked one. But in fact, in this case, because there's a neutron star and the neutron star emits copious neutrinos in this direction is affected by neutrinos in the later phase. This can be more clearly seen in terms of electron fraction entropy per baryon. In this case, as you can see, the entropy per baryon in the orbital plane is low, meaning the less importance of the shock. But on the other hand, we can see neutron heating component. And in this region, the electron fraction becomes higher due to this absorption of neutrinos. And I will have a talk on these topics next week. Thank you.
Do you want to comment on Brian's ejecting some of the accretion disk?
Comment?
Well, I think
could that be an additional source?
Yes, could be.
I think he would say that to get the weak art process, I don't need the accretion disk. And I would say,
so, but
in the sense that, I think the problem with the previous models of the dynamical ejector, as he was saying, was that you only get a third art process.
People try to make
but the weak art process you can make in supernova.
Yes.
No, but there's a universality.
You see co-production with
yes, yeah.
Yeah, but how do you avoid making the weak art process in supernova?
So maybe
you almost necessarily have to make it.
Yeah.
Why do we have to?
How do you
because
not?
They happen.
They make neutron stars. They blow winds.
No, but why there is an art process, a weak art process?
So the winds will be enough. Well, you could argue that you.
Okay, but this is, I would say, it's not established at the moment. I think there are.
Well, we're producing the neutron star mergers too. We just said we're getting a weak R process from the wind from the proto-neutron star. How do you avoid making any weak R process, the first peak in a supernova? You can't tell me that it doesn't have a neutrino-driven wind.
And
no, it does, but it's
if why
so far the simulations get to the proton-rich environment.
yeah, I think
They do if they're if they get the wrong
So I think
anti-electron.
I think the proton-rich environment proton richness
Yeah.
is probably in error, and they can go
Yeah.
back and fix the
Yeah,
error, and they
so-
will get some small
So-
YE less than 0.5.
I mean,
rather.
there's
But
papers
is it
already
enough?
on that. So I
Is
think
it sufficient for the...
yeah.
how deep can you go? I think it's still a question, how deep can you go? Deep in YE. Let's say it's true, up to 2 or 3 years ago the answer was 0.55 and then no way to get that process. Then there is still a good excitement about the fact that with taking into account the nuclear physics carefully you can get low, but I think there is still no convergence about if you can go to 0.49 or 0.42. I think this is what
Yeah.
I meant. I don't think it's a moment it's sorry?
Yeah, we don't know the answer to it, but
Yeah,
I'm
yeah.
saying that it would be, I think it would be premature to say that, if you did all the physics right, that supernova wouldn't produce the weak R process. I would suspect that it would produce some weak R process, and
Yeah.
you need some other
But-
mechanism to suppress it.
So with these chemical evolution calculations, now I know that the strong R process is pretty robust and the weak R process is variation. Is there any evidence in the data for a correlation or a co-production between those two in the sense that is it consistent?
yes,
Is it consistent with the supernova making the weak R process?
yes.
And then
yes.
just there being mergers just producing the heavy R process? Is that
So
that is okay?
Yeah, okay. This okay because this universality is from atomic number of 40 to the 90. This means that in terms of this peak mass number 90 about 90 to 82 here is universal. And this usually, if you use the usual parameter set, it is even difficult to make a second peak.
Parameter set for supernova? Or
Yeah, supernovae.
Right. You're saying that the abundance is. So my understanding
Yeah,
was
yeah,
that
yeah,
the
yeah.
second and third peak were robust, and then there was more variation.
Yes.
In the 100 range. But I thought there was still a correlation between abundances of the second and third peak and the first peak.
Yes. But the correlation between first and second is not so tight.
Okay.
And also the mass range is limited, and so most abundant part is not constrained by the low matter stars. Okay, so from here to here, and but the previous problem is that even in this region, we cannot satisfy the robust universality. In the previous binary neutron star merger simulation.
Okay, so you're saying that if I say that the second and third peak are produced in neutron star mergers, you think we have to also produce the first peak?
Yes. So
In the mergers. You're saying the data requires that.
yes, we don't have data for
We don't explain the 80 or 90 stuff. That
Yes,
can come from
yeah.
supernova. You're
Yeah.
saying we have to have
Yes.
the first peak in the
Yes,
mergers.
yes,
And so I think
yes.
to answer Chuck's question, I would say that this lower YE or higher YE material producing the weak R process could come from the accretion
Yeah.
disk outflows
Yeah,
later in the
yeah,
evolution.
yeah.
And you would say
Yeah.
for soft equations of state, it
Yeah,
could come
yeah,
out
yeah.
in the dynamic
Yeah.
region.
And also interestingly, in the case of soft equation of state, the hypermassive neutron star soon collapse into the black hole. In this case, oops. So that we don't see any clear wind component. This is because the most strongest neutron emission region is the surface of neutron star, proto-neutron star, hypermassive neutron. But such a strong neutron emission region is swallowed into the black hole, and then neutron luminosity decreases. In this case, we don't see any clear wind component. Yeah.
I have just a question about the simulation. At the beginning, why there is a sphere around?
Yeah. This is the okay. This is the because okay. So in our simulation, grid-based simulation, we must put some atmosphere,
Okay.
and the atmosphere is decreased in yeah.
Just somehow this should be also the place where the GRB is produced. Is it which constraint? Because
Okay.
for the density, let's say we are putting just where we expected the GRB to form, and we are putting a density that, if I remember correctly, the previous plot is 10 to the 8. And I think that already something like 10 to the 6 makes the production of the GRB, at least for neutrinos, impossible. If we put 10 to the 8, I think that this...
I think
Yeah, the 10 to the 8 is not...
The atmosphere is smaller than 10 to 8.
But let's say the
I know.
plot where it showed the simulation, and I asked what was color coded, I think the answer was the density. And then I checked just 50, 60 kilometers above the center of the domain, and then it was 10 to the 8. And this is the region where neutrino potentially could deposit energy to drive the wind. But then if the density is 10 to the 8, the wind would
No.
Yeah, 10 to the 8 is just
At that paper, we don't care about the energy deposition mechanism.
But that is a hypermassive neutron oscillation. So
Just check how we can obtain tight collimation. Okay. In the case of the previous simulation, we don't have any mass rejection in the meridian direction. But still, we must have collimation of less than 10 degrees, according to the latest observation by Edo.
Yeah, in the case of Shen, at least in the YE, it looks to me that there is a clear funnel, right? In the other
No. In our case, even in the Shen case, the result is similar to this one.
So it's still very isotropic.
Yes, like this.
But how can I get a collimation there?
No, collimation is due to this because there is a matters due to this matter pressures, the jet can be collimated. Otherwise, really.
But then there is a density of gradient. There is a density of pressure. It's because there is a density of.
Yes.
gradient. But what is the density in the funnel?
So is there a disk being formed there at the center?
Here,
Yeah.
this is the proto-neutron, hypermassive neutron star, and from the neutron is emitted from the hypermassive neutron star in this direction.
He's asking,
Is there an accretion disk around the hypermassive?
Yes.
In this model, the black hole.
Black hole is not formed.
In this
But-
this model.
But still, we have some disk around the hypermassive neutron star.
around it.
Yeah. Toward, yeah.
Or it's doing what Brian was saying, it's going off that disk.
So this correlation between dynamical ejecta and neutron star radius
Yes.
is because the softer equations of state result in higher temperature.